Okay, we will discuss now how LPC2148 interrupts can be used to develop the applications. So basically, what is an interrupt? So an interrupt is a signal sent to the CPU which indicates that system event has occurred which needs immediate attention. An interrupt request, that is an IRQ, can be thought of as a special request to the CPU to execute a function, that is interrupt service routine. So whenever interrupt arrives to the CPU, it stops the main program and executes the ISR. Once ISR is finished, it continues with the main program. So let's understand what is the support provided by the LPC2148 for performing the interrupt programming. Now, so if you look at the LPC2148 microcontroller, inside it has got a core manufactured by the ARM7 TDMIE. So we have learned when we studied the architecture of ARM7, it supports two types of interrupts. One is IRQ, other is a FIQ. IRQ is a normal interrupt request whose priority is less than the FIQ. So FIQ has got a higher priority compared to the normal IRQ. So since ARM core provides only two interrupt types or interrupt pins, there is a requirement of lot of interrupts from the within the peripheral LPC2148, that is a chip, from the different peripherals, and also from the external to the IC. What I mean is the core has got only two interrupt types, IRQ and FIQ, but the interrupt request is coming from lot of sources present inside the LPC2148 chip. Timer 0 wants interrupt, PWM wants an interrupt, peripherals wants an interrupt. So number of peripherals present inside the 2148 wants an interrupt, but there is only two interrupts are available. So to manage multiple interrupts coming from the different sources within the chip and generate one of the two interrupts to the microcontroller core, there is a block inside the LPC2148 chip that is called as vectored interrupt controller. So what is a vectored interrupt controller? So this jobs. Number one, it accepts multiple interrupts. So in this 2148, we say that there are 32 sources which can generate an interrupt, and then select any one of them and generate an FIQ, or select any one of them and generate IRQ to the core. So that's the first job. So what is the first job of VIC? Many interrupt requests are, so make them select any one of them and generate an interrupt to the ARM7. Second job, when more than one interrupt request has come to the vector interrupt controller, it has to do what is called as priority. So that means that if 5 sources generate the request, only one of the 5 has to be identified and that has to be passed to the ARM core. So on what basis we select one of the 5? So priority is assigned to all the interrupts which are generated and passed on to the VIC. That is the second job. What is the third job of VIC? We are doing very important program. I do not want an interrupt to disturb the program which is run by the ARM core at the moment. So VIC provides a facility to enable or disable the interrupts. So summarizing, the VIC vectored interrupt controller has the 3 jobs. Number one, it selects one among the multiple interrupts. Number 2, it prioritizes the interrupts. Number 3, so it enables or disables the interrupts. So now we have understood that what is the job of VIC inside the LPC2148 chip. Now all the interrupts which are generated and sent to the VIC can be classified into two types. One is it is an FIQ type of interrupt. So other one is it is called as IRQ type. In the IRQ, there are two types are available. So what are the two types? Number one is called vectored interrupt request, or we say vectored IRQ. Other is called as a non-vectored IRQ. So summarizing, interrupts which are coming to the VIC or interrupts are generated by any peripherals inside the 2148 will be of two types, either FIQ or IRQ. In the IRQ, there are two types are there. One is called vectored IRQ, other is called as a non-vectored IRQ. Now, since these three types are available, there is a priority is being assigned to all these interrupts. FIQ has got the highest priority, IRQ has the second priority, non-vectored IRQ is the lower priority. So now we have understood that interrupt types and their priority. Now, so I said inside the LPC2148, you have got a lot of peripherals. These peripherals, when some event happens, they will generate an interrupt to the core, to the VIC. So let's understand one or two. Let's say timer. Whenever timer reaches the match value, so we have understood how does the timer works. Inside the timer, there's a timer counter is there, which keeps on counting. Whenever the count value reaches to the match value, then some initiation should happen. So what are the three initiations possible for every timer? Either it can stop, it can reset, or it can generate an interrupt. So for an interrupt, timer 0 contributes one interrupt. Similarly, timer 1 contributes another interrupt. So like this, every peripheral present inside the LPC2148, when certain activity happens inside, they generate an interrupt. For example, UART. UART is a way to communicate to the PC. The microcontroller communicate to the PC. Whenever microcontroller receives the data from a PC, it can generate an interrupt. So that is mean that whenever the data is available on the receiver, it can generate an interrupt. Like this, every peripheral inside the 2148, when certain activity or event happens, it generates an interrupt. So how many they have classified? They specified that there are 32 sources are there. From there, these interrupts are generated. So those are listed in this one. So I have taken this slide from a 2148 user manual. Now understanding how to develop a program which is interrupt enabled. So for that, I have to understand what are the important registers present inside the vectored interrupt controller. Number one, interrupt enable register. Interrupt enable register is a 32-bit register. So this register has got a 1 bit for one peripheral. For example, if I want to enable interrupt generated from the timer 0, so I have to go to the bit number 4. I have to write 1 here. So 1 means interrupt is enabled from that source. 0 means interrupt is not enabled. Reset value, all the interrupts are disabled. This is very important when you develop a program. Interrupts will not generate automatically to the VIC, and VIC will not recognize, because why? The reset value is always 0. So whichever peripheral you want the interrupt to be generated and ISR to be called, the corresponding bit corresponding to the peripheral to be made 1. So to recognize the timer 0 interrupt, so I have to make this bit is equal to 1. Like that, for every device, 1 bit is associated here. Now we have understood interrupt enable register. Now let's go to the second register called as interrupt select register. So what is the meaning of interrupt select register? I said there are 32 sources are there. Each of the source generates an interrupt, but this interrupt whatever generated can be one of the three types. The timer 0 generates an interrupt. You can call that interrupt, or you can assign that interrupt of type FIQ type, vectored IRQ type, or a non-vectored IRQ type. So generally there are two types, FIQ and IRQ. So one bit is provided in the vector interrupt select register. That bit decides whether the interrupt generated from a particular source is of type FIQ or a IRQ. by default, everything is IRQ type interrupts. So that means that by default, interrupt select register, 32-bit register, all the values are 0. So any bit, if you make it 1, that interrupt you are assigning as a FIQ type. So interrupt select register is a 32-bit register. 1 bit is provided for every source. So that interrupt from that source, you can call it as a IRQ or FIQ. Now, let's go to the next register. So these two registers, vector control and vector address register, they are used only when the interrupt you are assigning them as vectored IRQ. We have understood that any interrupt generated will be of type vectored IRQ or non-vectored IRQ. But all the 32 can be made FIQ possible. All 32 can be made as a non-vectored also possible, but vectored, there is a limitation is there. Only 16 among the 32 you can make them as a vectored IRQ. So let's understand, if I assign interrupt from a particular source as a vectored IRQ, what are the regulations or what are the registers available and how to configure them? Let's understand that. So I said there are 16 vectored IRQs are possible. So generally they'll be called as slots. So if somebody says how many vectored IRQs are there, people also use what called as IRQ slots. There are 16 vectored IRQ slots are there. That means that timer 0 can be configured as one of the vectored IRQ slot. So if I interrupt is generated from a timer, I can treat that timer as an FIQ, as a vectored IRQ, or as a non-vectored IRQ. Let's say now I want to configure the interrupt generated from a timer 0 as a vectored IRQ. So then what should I do? So for that, they provided two registers called vectored interrupt controller, VIC, vector control register 0 to 15. That means that there are 16 vector control registers are there. One register for one IRQ slot. Similarly, VIC vector address 0 to 15. That means that there are 16 vector address registers are there. So each register, one register for one IRQ slot. So that means that if I have 16 IRQ slots are there, every slot will have two registers. One is called vector control register, other is called the vector address register. So now let's understand what is the meaning and why it is required like that. Now I have in this diagram, I have used the slots here in the picture. So slot 0 to slot 15 is there. As I said, every slot will have one control register, one address register. Let's say now timer 0, we are treating this as a vectored IRQ interrupt, and this I have to assign now to one of the 16 slots because we have 16 vectored interrupts are supported. Each is there called as slot 0 to slot 15. So which slot I have to use? Let's say I taken a decision, this interrupt from a timer 0 I have to use as a vectored IRQ. So I can use any one of the 16 slots. There's no restriction is there. So arbitrarily you can choose any slot. But if there are two devices are to be used as a vectored IRQ slot, so then the question comes, if both request from timer 0 also comes, request from SPI device also come, which is to be taken? So then the priority, you should know that. So priority of the slot 0 is higher than the priority of slot 1. That means that the priority decreases from slot 0 to slot 15. Slot 0 has a highest priority, slot 15 has a lower priority. So if there's only one device is there in your project, you can assign the interrupt to any of the slot. That does not make difference. That's how we develop the program now. If there are two devices are there, then choose which is of higher priority is required, assign to the higher to the slot which has got a higher priority. That means the slot number low. So now let's say timer 0 I have to give highest priority. So I wanted to assign the timer 0 to the slot number 0. Then what should I do it? Whenever interrupt is generated from the timer 0, there are two things should happen. Number one, this slot should know this slot is being mapped to this device. So there is somewhere inside this register called vector control register, we should specify the device who is attached to the slot number 0. The slot does not know that. So which device among the 32 sources has been mapped to this slot? So that is how they have provided a provision of 5 bits in this register, because why 5? 2 to the power of 5, 32. So 32 sources are there. So in that 5 bits, I should indicate the source from where this interrupt is generated. So all devices, that is 32 sources, has been given a fixed number. Timer 0 number is 4. It starts from 0, 1, 2, 3, 4. So we can just check that. So if you look at this, the register slots, what we have here, you can just see that. So timer 0 slot number, sorry, source number is 4. That means that every device which generates an interrupt, so has given a number. Timer 1, the source number is called as 5. It's a fixed. It's not going to change. So for a given microcontroller, so timer 0, the number of this, so the source number of the interrupt from the timer 0 is called as what? The 4. So now I know that if I want to assign timer 0 interrupt to the slot number 0, I should first of all find out what is the number of the source. So now I got that one. So now what I will do, I will go to the vector control register. So this register provides, it's a 32-bit register. In that, the first 5 bits, D0 to D4. So to be indicated, the source of the interrupt, which is mapped to this slot. In this case, we know it's a number 4. So that's why I have written here 00100. So it's a 4. So it's a 4. So if I would have taken the slot 0 mapped to the timer 1, then I should have written here 5. So since timer 0 source number is 4, I have written 4 here. This is the first job of a VIC vector control register. Next, the second job is there in the vector control register. The D5, there's another bit is provided. This bit controls enabling, disabling of the slot or the channel. So there are 16 channels are there. Each of the channel can be enabled or disabled at any moment of time. So if I write D5th bit is 1, that means that slot 0 or the channel 0 is enabled. So this is what is the meaning of VIC vector control register. So now let's understand. So what is the purpose of another register called as vector address register? Now a given channel has got a 2 register. One is a control register, other is a address register. So whenever an interrupt is generated from the timer 0, so the channel knows that, the slot knows that it is from the timer 0 because you indicated in the bits 4 and it's also enabled. Now it has to stop the program what the LPC2148 is executing now, the main program, and execute an ISR related to what? Related to the timer 0. So you would have stored the timer 0 ISR along with the main program. Now, how does this slot 0 or channel 0 knows that where is timer 0 is located, ISR is located? That is why they have provided one 32-bit register where the address of the ISR is stored here. So that means that every slot, vectored IRQ slot, has 2 registers. One to map the source, one to store the address of the ISR. So that is why it's called as vectored interrupt. So what do you mean by vectored interrupt? Means there is an address associated with every interrupt. Address means the place where ISR is located. So the programmer has the freedom to store ISR anywhere in the program. Only thing is the starting address of the ISR has to be loaded into this one. So this is how the two registers associated with the vectored IRQs are used. Now let's go to another register. So now we have understood vector control register and vector address register of the 16 slots. Now there is another register called as vector default vector address. So if you look at the last this register, so what is the meaning of this one? I said interrupt is of three types: FIQ, vectored IRQ, or a non-vectored IRQ. If you configure non-vectored IRQ, as the name says, is non-vectored, that means that there's no way you can specify the address of the ISR for non-vectored interrupt. But where does when the interrupt generated from the non-vectored source, where does it jumps? There's a one address is available, which is called as default vector address. That means that if I have configured, let's say 16 peripherals, timer 0, timer I2C, like all of them as a non-vectored, for all the 16 peripherals, there is only one ISR is available. There is only one ISR is available. So this ISR is not pertained to one source. It is a common. It's a common for, let's say, 16 peripherals, which I configured as a non-vectored IRQ. So the one common ISR whose starting address is being specified in the VIC default vector address. So then you may ask the question, if any of the interrupts from the non-vectored IRQs generates, how does the program knows that is, so from which source it has generated? So inside the ISR, you have to read what is called as status register is available, vector status register. From there, we have to read the bit, find out so which has generated an interrupt, and then I should be able to execute, call the, another service routine, or execute the logic required for that one. So that's why it's called as a non-vectored interrupts. So there's IRQ, but they are non-vectored. There's only one ISR for all the devices. So that has been stored, is to be stored here. So now we have understood all the registers related to the VIC. Before we start programming, let's revise. Vector VIC interrupt enable register is used to enable or disable interrupt generated from the 32 sources. VIC interrupt select, it's used to configure the interrupt generated from every source as IRQ or FIQ. So VIC vector control and VIC vector address registers, two registers present for every vectored IRQ slot. So one contains the source which generates an interrupt, and one bit is used to enable or disable the channel. Vector address register hold the starting address of the ISR. So vector default address is a starting address of the one common ISR, which is meant to serve all the non-vector IRQs. So now let's write one program. So interrupt service routing. Now what are the requirements? Now I should take a decision. I am writing an interrupt for which peripherals. So now I am writing an interrupt for a timer 0 peripheral. So in the theory exam also, syllabus also, we are confined to timers. Let's understand how to do it. Now I want to generate a 50 Hertz waveform using this program. So 50 Hertz waveform means the clock cycle, the time period is 20 milliseconds. So on and off time becomes half of that, 10 milliseconds. Now, since I'm using the timers to generate this waveform, I have to load the required value into the match register. Timer 0 has got 4 match register, MR0, 1, 2, 3. I have selected MR0. I have to generate 10 millisecond time. So after every 10 millisecond, I'll make one of the bit, let's say P1.16, high and low. After 10 millisecond, I'll make it high. Again, after 10 millisecond, I make it low. So this is a logic I want to write to generate a square waveform. So I should know when the 10 millisecond is completed. So for that, I'll use timer 0 with an interrupt. So now to produce 10 millisecond, we know that in the timers we have studied, the value to be loaded in MR0 is what? 10 millisecond divided by the time period of peak clock. So we are assuming peak clock is 15 megahertz. So time period of one peak clock is 1 by 15 megahertz. So it's 1,50,000. So I'll be loading 1,50,000 in the MR0 register. We know that in timers, whenever you load the value 1,50,000 in the MR0 register, whenever the timer counter starts counting 1, 2, 3, 4 and reaches to 1,50,000, so it generates an interrupt. So that is a event I have to catch now. So now let's write two programs. So what are the two programs I'm supposed to write it? So I will just show that. So the program itself, I'll go to the key. So I have just written that program. Okay. Now, what are the things I'm supposed to do it? Number one. So before I write the program, I should be very clear. There are two programs exist. One is a main program. One is an ISR. The name of the ISR program is timer 0 ISR. I called it. It can be any name. It can be given any name. Always ISR has void argument type because you are not calling the ISR. ISR will be called at the hardware level. So there is no question of user calling it and passing the arguments. So one of the feature of ISR is what? No arguments. And always return type is also void because you are not returning, you are not calling. There's no question of return. So return type is void always. The what value you pass is also void. How do you differentiate a normal function and ISR function? There is a keyword. So this keyword, so underscore underscore IRQ or underscore underscore FIQ. Since I am writing now interrupt service routine for the timer 0, now it is an option for me to configure timer 0 interrupt as FIQ, vectored IRQ, non-vectored IRQ. So I have taken a decision here. I am configuring timer 0 interrupt as vectored IRQ. So that is why I just specified here IRQ. So it is a vectored or non-vectored. So I am configuring as a vectored IRQ. Now, so there are two programs there. One is a main program, other is a IRQ called by the hardware. There is a hardware interrupt, not programmer is calling this function. Now let's understand. Now what I supposed to do it? Now the first thing I supposed to do is I will do all the things which is required for the timer. So now since I'm using P1.16 to generate the waveform, I'm configuring the pin as a output. So this is the one thing. Next, timer. So first I'll stop the timer. Timer control register is used to start and stop the timer. I stop the timer because I will do initialization of so many registers. After finishing that, I will start the timer. You can just see that I'm stopping here. And then after doing all the initialization, I'll starting here. Now, after stopping, what should I do it? Number one, you have to configure the MR0 register to generate an interrupt when it reaches the match value. We know that MCR register provide 3 bits for every match register. So those 3 bits control after reaching the match value, either I should stop, I should reset, or I should be able to generate an interrupt. So 3 bits are there. So now I don't want to stop it, so I'll make it 0. This is reset. That means that every time it reaches the match value, I want to reset and restart from the 0 because I want to generate a continuous square waveform. So that is I make 1. Now the last bit. Last bit is what? Interrupt. That means that whenever I write 1 here, it generates an interrupt so that it will go to the VIC. So then ISR will be called. So unless you make this bit is equal to 1, ISR will not be called at the hardware level. So whenever you write an interrupt, make sure that the interrupt generation logic to be enabled. So here it's controlled by an MCR, we are enabling. So whenever the timer counter reaches the match register, interrupt will be generated. So next, since I want to produce the match after 10 millisecond, I am loading 1,50,000, which I have calculated now. So I am loading the TC with a 00, even not required. So first time only it's required. So you can comment this statement also. So I'm just loading 00 to start with from 0. Now I finished initialization of all registers inside the timer. Now I have to initialize interrupt related registers. Number one, we have to enable the timer 0 interrupt. We know that this is the 4th bit. So 4th bit means you can just see that. So this bit corresponds to the 4th bit. This bit corresponds to the timer 0 device. So the moment I make it 1, that means that this interrupt from the timer 0 is enabled. So now this will be writing It's nothing but. So now this value enables timer 0 interrupt. Next, since I have decided to treat the timer 0 interrupt as a vectored IRQ, that is type 2, so I will be using one of the 16 slots. As there is only one device is there, you can use any slot. That means slot 0 to slot 15 I used. So just arbitrarily, I have taken a slot 5. You can use anything. So address 5 is one register of the slot 5 where we show starting address of the ISR. So this is the name of the, we know that in the C language, the name of the function itself represent an address in a C. So I'm just typecasting as an unsigned long 32-bit address value and storing in this register. So now it's a vectored. Vectored in the sense it points to a particular place. Now this slot should be assigned to timer 0. We know that. So it contains 32 bits. In that, the first 5 bits indicate the source from which the interrupt is mapped to this slot. Since it's a 4, we know that in timer 0 is a 4. I have written 00104. Now, 5th bit is enabling this channel. So now, so this value becomes 24 now. 24. So now, 2 registers which are required to configure IRQ interrupt is being done. Next, now since all the initializations for the registers for timer 0 and the interrupt related registers done, now we'll start the timer. So T01, now timer starts. Look at the beauty of this program. No code is there in the while 1. That means that without writing a single code in the while now, automatically the square waveform of 50 Hz will be generated with the help of timer and interrupt. See, you can write any logic here. The background automatically is happening. That means that advantage of delegating the work to the timers and the interrupts. Now the programmer is free to do any job. You don't require to think, is it happening? What should I do? Anything I have to do after the 10 millisecond? Nothing, because it is taken care already. You initialized everything. So no code is there in the while loop. It's an indefinite, but still the waveform will be generated. So we will see that now. So now we will finish writing ISR. What is there in the ISR? Number 1, this ISR will be called whenever the timer counter matches with the MR0 register. That means that it reaches 1,50,000 code, 1,50,000 count, then the interrupt generates. At that time, this program will execute it. So after 10 millisecond, it comes here. Then what should I do it? So every 10 millisecond, I have to make the P1.16 high and low. See, one time I'll make it high. Again, after 10 milliseconds, it comes. I'll make it again low. So that is why I used one variable X. So I made this variable as a global variable because the value should not be changed. If I declare inside, every time I use a variable, it assigns to the standard value. Either you can make this variable static variable or as a global variable. Now, to begin with, I made a 0. Every time it enters, I'll complement the value. If it is 0, I will set the ping to high. If it is 1, I'll make it 0. That means that one time you're setting it, second time you call the ISR, you're making it 0. So it complements. Now, what is the end of the ISR? It's very important for any microcontroller. At the end of the ISR, you have to do some housekeeping work. So this enables again accepting the interrupt for the second time. If you don't do this housekeeping work, interrupt will be called one time and execute ISR will be executed only one time. After that, further it will not be executed. So what are the housekeeping you have to do it? There is a requirement for the timer 0. There is a register called interrupt register is there. Now the bit has been set whenever the first time interrupt is generated. Now you have to clear that bit. So writing 1 to the same bit position, that means that interrupt register has got a bits for every match register. So the bit 0 is for the match register 0. So that bit, it was set when the interrupt is generated. Now you have to clear it. Writing 1 to the same register, it clear the interrupt so that it's ready for accepting the interrupt second time. So I've just made the housekeeping required for the timer 0 interrupt so that I'm ready to accept the interrupt second time. Now, what is the housekeeping you have to do for the VIC? See, vector interrupt controller is available to service the interrupt for all the sources, 32 sources. So every time you service one ISR, you should make that hardware, that priority hardware, ready for servicing the next interrupt. You have to clear the previous interrupt. Say that ISR, present ISR is completed. Now you should instruct to execute the next ISR based on the priority. So how to do that? So there is a register called VIC, vector address register. You have to write 00 to that one. It is also called as end of interrupt. So writing 0 is called as end of interrupt. That means that you're telling to the VIC, that means that current ISR is completed. Get ready for the next ISR execution based on the interrupts available at that moment of time. So now I have finished ISR writing. I also finished main program writing. So now I'll execute this program. I'll compile. So there is no error is there. Now I will execute that in a simulator. So now I have dragged two peripherals here. So one is GPU, because the P1.16 keeps changing because it's a square waveform. So this bit should change. To observe that, so I have dragged logic analyzer here. So I have set one pin observation here. You can just see that it is nothing but P1.16. It's a bit, it's a digital bit. I just close it. So now, so the logic analyzer should display the waveform generation, even though the code in the main program is what? No code is there here. So we will just observe that now. So now I'll run the program. I'll run the program, full program. Now see that waveform generated. See that there is no code here. There is no code here, but still it's happening. So you can just see the bit is also changing. So how it's happening? Because of the interrupt, because of the interrupt concept. So if you want, you can just measure the waveform also. So I will just say stop it. So how do you measure it? So click at the beginning of the waveform reference, then go to the end of the cycle. Just keep the cursor there. You can see that 49.808. So approximately it is exactly 50 hertz. 50 hertz. So this is how you can generate many activities in the background by pushing the works to the interrupts. So this completes topic on the interrupts. So we have identified what is an interrupt, what are the interrupt types available in this one, what are the minimal registers we should understand to write the interrupt program, and how to use an interrupt to generate a waveform using a timer 0.